Okay, in the second part of the problem, you're asked to use the circuit shown here in this diagram to implement the state diagram. So if you'll take careful note, this circuit diagram uses a Shannon decomposition for inputs dA and dB. So here's dA and here's dB. All right, so we talked about a Shannon decomposition back for exam 1 material. And so the way we get started with that is to reproduce the Carnot maps for dA and dB like we had done in the previous step. All right, so the next step then is to identify the appropriate squares in the Carnot map corresponding to the select lines in the two multiplexers. Okay, so let's go through that. All right, so to get started here, I'm going to put on the highlighter. And the first thing I want to do is I want to look at what is the region on the Carnot map where QA and QB are both 0. So we can label this 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, just the normal Carnot map labeling. Okay, so I'm looking for the place on the Carnot map where QA is a 0 and QB is a 0. So I can check out the bits here. And I see QA equals 0, QB equals 0, QB equals 0. These squares correspond to 0, 0. Okay, so that would be true on both Carnot maps. All right, so looking at that, I now have essentially a one variable Carnot map involving X. All right, so I see on the first one, there's 2 zeros here. All right, so for dA, I would tie the 0 input to simply 0. All right, for the second one, I have just a one variable Carnot map. I would circle this. What does that correspond to in terms of X? Well, that's on the X bar side of the map, so this would be X bar. All right, so that takes care of QA, QB equals 0, 0. Okay, next we could change colors here. And let's go with purple. So for this one, let's let QA be 0 and QB be a 1. Okay, so QA equals 0 corresponds again to this upper row. All right, so it's an overlap. But QB equal 1 are these two squares. All right, so it's right here. That's true on both Carnot maps. All right, so looking at that reduced Carnot map that's now just a function of X, okay, I can read this. If I circle this 1, that's in the X region of the map, so this would be X. All right, if I circle this one on the B map, that's on the X bar half of the map, and so this would be X bar. All right, let's continue on. Now let's look at 1, 0. And we'll change colors. Okay, so 1, 0, here's 1. All right, and then where QB is a 0 are these two squares. And so this region on the Carnot map corresponds to 1, 0. All right, the same is true for both Carnot maps. All right, so now it's just a matter of doing a circling. All right, and so my pen just died. Give it a second. And so on the A flip-flop, you have 2 1s. All right, so in that particular case, line 2, because we're looking at 1, 0, would be tied to a 1. Oops. And on the second one, I do this circling, and that's on the X side of the map, so this would be X. Okay. So that leaves us the other two squares. I think it's obvious where those are. It's the ones that haven't been colored yet. And so let's switch the highlighting. Okay, so if we switch the highlighting on that, we could use green. These two squares are what we are worried about. There's zeros appearing on the QA flip-flop, so this line would be line 3, corresponding to 1, 1, would be tied to a 0. Okay, so what we're doing here is we're switching to 1, 1. And this would be green. Okay, so that's a 0. And then if I did the circling on the Carnot map, that's in the X region of the reduced Carnot map. So this would be X. Okay, so once you have this structure for the circuit with the multiplexers handling the next states, it's just a matter of selecting the input lines based on X to implement the state diagram. So that's the technique. Again, you look at next state, make a Carnot map for the DA and the DB inputs, and then partition this out just like we did for Shannon decompositions before for exam 1.